Hello, Mr. Eric. How are you today?
Good.
Good. Okay, so you play chess, right?
Yeah.
Okay, so
Well, not really.
not really. Okay, that's fine. So we have a chessboard. Chessboard, with the empty stairs and with the knight and one king. Let's say we have one king here. Okay, only one king. Only one king. Okay, but there could be many knights. Okay, knights. Yeah, you know the knight. You know what's knight?
It's like a soldier or something.
Soldier and riding on a horse, right?
And with helmet and.
Yeah. So knight, yeah, like that. The horse.
I can draw a knife.
Okay, I don't know how to draw. Yeah, with the sword. Okay. Yeah. You can use this one. Okay. So let's use the edge, yeah, because it will be horse edge. Edge. So it could be 2 edge, 3 edge here. Okay.
Blah
Wow. Okay. Okay. That's very abstract.
blah blah.
Okay. Okay. Yeah. Got it.
And the tail.
You call it horse? Come on.
And neck.
Okay. Let's yeah. Okay. So you know the horse. In Chinese chess, how do we move the horse? Where can this jump? Where down? Okay. So basically, if this is x, this is y, right? The offset of x could be 1, y could be 2, or x equals 2, y could be 1, right? So it could be like, one step to the right and 2 step, right? 2 step to the north, right? Okay. So they are 3. And how many moves? What's the minimum number of moves in order for any of the horses to capture the king?
1.
Yeah, well done. Okay. And how about if I don't have this? How many? What's the minimum number of moves?
2.
Yeah, 2. Yeah. Okay, you got it. Yeah. Because look, this one, in order to capture this, how many moves it requires? Yeah.
3.
3. Yes. Well done. 1, 2. No, 1, 2, 3. Okay, 4 moves. Okay, 4 moves. For this one is 1, 2. Okay, make sense? Yeah.
Yeah.
So today's task, we have one king on the board. Yeah. This is like a metric. We can represent this as a metric, 2-dimensional metric in Python, and where 0 is empty. Okay. 1 is king. 2 is the knight. Okay, knight or horse, Knight or horse. So we want to find out, the task is that we want to find out the minimum number of moves for some knights to capture the king. The horse cannot jump on the horse. For example, if there's a knight here. For this one, it cannot jump here. Right? Make sense? Yeah? Because this place is already occupied by another knight, another horse. Right? Make sense? Yeah? What's your question? Yeah? You got a question? Yeah?
No,
Sorry?
I don't have a question.
You don't have a question, okay. That's fine. But you understand what I'm talking about, right? So we want to find out the minimum number of moves for some horse to capture the king. Okay. So let's put it simple. If there's only one horse, yeah? If there's only one horse, let's don't look at this. What's your approach to capture the king if there's only one horse? If we want to find out the minimum number, we can do what kind of search? What kind of search can we do? Come on. Breadth search, well done. Why is breadth search? Look, here, you have your horse here, right? Your horse here. And then the next move, you can jump another to here. How many nodes are there for the next move? In the ideally, how many of these? What's the maximum number of moves for the next move? Well done, 8. Okay, 8 moves, yeah, because if you're here, you could have a direction. Yeah. So like if any of these is the move will be capturing the king, then we find the shortest. Yeah. For the breadth search, it usually can be used to solve the shortest, right? Because that's the way I travel the tree, level by level, right? Am I right?
Yeah.
So when I visit the node, for example here, and this is the king. If I found here, and I already know like the two moves, right? Because I always expand the levels by level. And when I visit the king, it's always the guarantee the shortest. Make sense?
Yeah.
Wait up. But depth search may not give the idea, right? Because look, if depth search could be somewhere here, this king will be here, right? When you get a king, it may not be the optimum, right? You could maybe take 10 moves. You need to travel all the trees and compare the moves to get the minimum. But for the breadth search, when I found the first king, it's already the shortest because I travel the trees level by level. It's guaranteed the shortest. The depth search, not the optimum. You have to travel the entire tree, because look, yeah, you may find a king, yeah, by following this path somehow. Yeah, you might find a king here, but you don't know. There may be some shortest path here, right? This is the optimal. When you find a king, you have to remember it. Okay, so I take 10 moves here. Okay, I take 3 moves here. So the shortest is 3 moves.
That's 2 moves.
Okay, 1, 2. Okay, yeah, makes sense. So look, there are many edge, many edge. Yeah, we already know how to solve this problem using breadth search if there's one edge, one horse. But how about many edge? We can repeat this as many times as possible, right? Yeah. If there are n edge, we can do. Look, we can do this. One solution, brute force, yeah, is that we try for each edge, we calculate the minimum number of moves to add k, and we get the minimum number, yeah. So you'll be like for edge in all the edge, yeah, edge in all the edge. This is all the edge. Then we do this answer equals mean answer, and then breadth search. Okay, breadth search. I start with this edge, right? And then return answer. Yeah? This is one way brute forcing. Yeah? Make sense? Make sense? Yeah, look, because we already know how to solve the one problem, the one king, or one horse to one king. The source to the destination. And we can repeat this h times. If there are n horses, we can repeat this n times. Right? But this is not optimal. Why is that? Because look, let's take the complexity, for example. If what's the complexity travel from source to the king? Yeah, it's n. If there are n rows and columns, yeah. If this is the n rows and columns. Okay, so ideally n rows and columns, and we can visualize this as a graph, right? We can visualize this as a graph. So this edge, can point to the vertex. This is the vertex. This is the vertex. And different. This is edge, and different vertex. Yeah, there are n times n square vertex, right? Then how many edges are there? I don't know. How many edges? How many edges for 3 vertex? How many edges for vertex? Do you still remember this? Do you still remember this? Let's so if there are n vertex, if there are vertex n vertex, how many edges possible? Look, remember a few days ago we talked about if the first vertex has edges to n minus 1
N minus 1
times n minus 2, yeah? Times n minus 3, yeah?
until 1.
Yeah. Okay. So let's consider there are n cells. Okay, not n rows and columns. There are n vertex and possible positions, and the number of vertex is n times because the first one is n minus 1, yeah, n times n minus 1 times n minus 2 times n minus 3 times 1, right? So it will be n minus 1 plus 1 times n minus 1 divided by 2. This is the number of possible edges. So this is n. So the number of possible edges is n, and yeah, this one is in the order of n square, right? In the order of square. If there are n cells, n possible positions, there are n square edges, right? So that means that because we only travel the same, we can use the hash set to remember the possible position we travel, right? So if I travel from here to here, the next time if I come back, look, if I come back, I don't travel again, right? Because this has been visited. Yeah, we use the notebook, yeah? hash map. Yeah. So the time complexity to travel from a pair of source to the destination is n square, right? Because only there are possible n to the power of 2 edges, and then we travel use n square. And if there are n horses, the time complexity will be n times n square, right? And this m, yeah, could be filled in this. So the time in the order of the possible positions. So the time complexity is actually n cubic, right? The time complexity we're using the Q, we're using the hash map. So it's all in the order of O(n), right? Got it? But can we do better?
Maybe.
Look, in order to shorten the time, we don't need to repeat this m times, right? We can put these m sources together at the beginning into the breadth search. So look, the breadth search usually start with the position, right? But we can start a set of positions, right? We can look if there are 5 edge here, right? I can put this 5 edge in the queue first, right? This is the takeaway today. Yeah, what did I just say?
This is the takeaway today.
Yeah, what's the previous one? What did I do?
Yes, this.
If I have 5 edges, I just put it in a queue, right? Remember we use the double-ended queue. We put it in a queue on the right hand side, in queue. We take it out, right? Okay? Yeah? We take it out. So instead of doing this 5 times, I can put these 5 positions into the queue. And then this is not like a tree anymore. This is like wow. So this I can travel this. So, and each one is 8, right? Possibly 8, yeah? Yeah? So it's still the same. If I found the king here, what does it mean? I still find the shortest move, right? Alright? Okay, so this is one optimization, right? One optimization. Okay, so as I said, there are many knights, 1 king. Can you think reversely? You know, what's reversely?
Think the places they could be together.
Yeah. So look, instead of going from the course, I can go from what? I can go from where?
For the kids.
Yeah, well done. Look, because there's only 1 king, right? So I can go from 1 king, and if I capture any horses, yeah, you'll be yeah.
These places.
Yeah. You'll be the shortest, yeah, because the direction, the edges, the graph. Remember the graph. If there's no direction, what do you call it? If in a graph we don't have direction, what do you call it? What's this graph? Undirectional graph. Yeah, undirectional graph. It's the same. Yeah, if you can capture the king from this position to here, surely the king can jump backward, right? The king can. Yeah, we just reverse it. The problem is the same. Yeah, we can just reverse these horses as the king, and K is the horses. Okay, makes sense. So because we have only 1 king, so the time complexity will be just O(n) squared, right? Instead of O(m) times n, because this could be in the order of n. Make sense? So we are reducing the time complexity from O(n) cubic to O(n) squared, right? Yeah? Yeah, makes sense? Okay, so but as I said, look, if we don't do that, we can still append the horses, many horses together to the queue, right? And this is called the multi-source breadth search. Do you get it? Multi-source breadth search. Make sense? Any question? What did I just say?
Multi-source in the
BFS search. What's multi-source BFS search? Can you tell me?
It's when you use
Lots of starting point. Yeah.
Yeah.
Previously we only have one king, one horse, and that's just single source BFS search. But now I have many places, and I can just do it. Okay, I will just implement this BFS search. Okay, it'll be easier. We use the WNDQ. Yeah. How do you define a WNDQ in Python?
DQ.
DQ. And what's Q? First in what?
First in, first out.
Yeah, first out. Okay. Define, let's say, minimum mean move. Okay, mean move. And we have a board. Okay, a board. You know the chessboard. Yeah. Right? So Q equal DQ. Yeah, because we use it WNDQ, but we are not sure what to put. Usually you put a root in binary search, right? In a binary tree, right? But we are not sure what to put here, so let's just initialize with nothing. So it's an empty queue. So now let's say the row columns is we just get the dimension of the board, yeah? The number of rows and the number of columns. Yeah? Yeah? Got it? Ball 0, okay? Ball 0. So yeah, and then we need to go through the board to put the. Let's start with the king. Yeah. For R in range rows. For C in range. What? What did I put here? The rows and what are these?
Columns.
Yeah, columns. And then look, if board RC is okay, let's define a constant. King equals, let's say 1. Empty could be 0, okay? And then horse, or no, knight, horse would be 2, okay? Something like that, yeah? If ball equals king, yeah, because we are capturing the king. King, there's only one king, okay? King, and then we just append it. Q dot append. Append. RC. Okay, look, we push two coordinates. What are these? What do you declare with these parentheses? What are those?
Tuple.
Tuple is called tuple. Okay. Okay, now this is the initialization. Initialization. We put the king into the queue. Yeah, into the queue. Yeah, because we were putting the sources, right? If you change, because there's only one king, we put in this one king. If there's only one king, we can break it here, right? We can just break. But if you try to append the horses, yeah, and then if try to, you can change this to horses and do it reverse way. Then this is called multi-source BFS search, okay? Multiple source BFS search. So after we do this, what should we do? After we do this, what should we do? And we can do this BFS search, yeah? Right? So first of all, we need to remember the number of remember the positions we have visited. So what kind of data structure can we use to remember the moves? What's it? Scene equals set, yeah. Okay, and then we can say why the queue is not empty, yeah? Why the queue is not empty? Now we okay, so because we want to remember the how many look, Eric. Yeah? Look. We want to remember when we visit this. This is the king, and then we want to visit here horses. We want to return 2 moves. Yeah, we want to return the shortest number of moves. So we can, because if we want to remember it, there are 2 ways of doing it. Because we can append the number of moves in a tuple, right? That's one way. Because every time you can expand the one node by node. And then you can remember the number of moves here. Yeah? Or as we talked about before, we can always we can always take all the existing numbers, the nodes in the queue, and then append their children. Right? We can take these 3 nodes all at once and push their children back to the queue. So in this case, every time I visited all the numbers, all the elements, all the positions in the queue, it's all belong to the same level. It's the same distance. Make sense? Yeah? So let's do the y queue, and we need to have the answer here. Yeah? Answer is the level. Yeah? Answer equals 0. Let's put it -1, so we can increment it immediately, so that will become a 0. Okay? So now we can do this. We can do the move. Yeah? For we can do the current. Current is RC equals Q dot pop left. Right? We take one. Actually, we want to take n elements out of the queue because there's number n equals length queue. As I said, we are taking everything in the queue. The queue. We are taking everything in the queue. We pop it out, right? And then we need to do this for underscore in range n. We're taking everything out. RC equals Q dot pop left, right? We're taking these out, right? Okay, so now look, we take this RC out. Then we need to check if it's the destination, then we can return answer, right? So if board RC equal what? We are starting from king. So where are we going to end? Terminate. Alright. We are starting from king. So if the board is what? If the board is what? We're starting from king, and then if we visited what? If we visited what? Knight or horse, yeah, the knight. Let's do it horse. Okay, if we ended the horse, then we can just return answer, yeah. Okay. Okay. Now I want to visit. Look, I'm at RC. I'm at this position as you know, yeah. As we know, there are A positions. Yeah, we don't want to visit all the A positions, right? Yeah. From here, we know possibly the maximum A children, right? We want to push. Anyway, we want to push these 8 kids. If it's still inside this board, yeah, if it's not outside, and if it's empty, right? Because it's not empty, then we don't need, right? Am I right? Make sense? So for let's say dr dc, this is data in A position. We can use the list of the coordinate, yeah, or we can use the array of coordinates. Let's use a tuple. Okay, 1, 2, yeah. This is offset, yeah. 1, 2, 1 minus 2, minus 1, 2. Okay, you can think about it, yeah. There are 8 of it. Okay, I'm not going to write all of it, yeah. You know, the A position. This is the coordinate, and then I need to say nr nc equals r plus dr, c plus dc. This is the next. This is the position of the next node, right? And then look, if these nodes nr and c are in a range, okay, in a range. How do we say in a range? Oh, I'm running out of space. So look, you can say 0 smaller than nr, smaller than rows, yeah. 0 smaller than nc, smaller than columns. If in a range, also the board nr and c needs to be what? Come on, you can answer this. nr and c needs to be what? I said. Look, if I'm here, I want to jump to the next position. If only if what? There are 2 conditions. If what? I want to jump it to the next position.
Yeah.
Yeah. So obviously we need to find out if this nr and c is not in the it's not in the scene. Yeah. Obviously we can say nr and c not in scene. Yeah, not in scene. If we're not in scene, I know we need to add it somewhere. Yeah, scene dot add nr and c. Okay. So do we need to check if the board is empty or not? Do we need to check? If we don't check, no, we don't need to check. Why is that? Because if we check it's empty, then you will never find look, you will never find the horse, yeah? Because, yeah, do you get it? If we check it's empty, and then if it's empty, we append it, right? We append it, and then you will never find the horse, right? Because we need to append its kit only if it's inside the board, if it's the next move is not at board, and if it's not visited, right? If it's not visited, make sense? And then return. If we can't find it, we return -1. Okay. Okay. This is called multi-source. Multi-source. If we starting for the horse, then that's multi-source. If we start from the king, that's still single source. Okay. That's still single source. Sim dot add NRNC and then Q need to append NRNC here. Q need to append NRNC. I didn't write it here. Q dot append NRNC. Next move, okay? Okay, so can one question for you, Eric. Can I exchange this? Can I swap these two? This is the king, this is the horse. Can I swap these two? And if yes, why? This is the what we are talking about in this lesson. We start from king, yeah, or we can start from horse. Can we? Yeah. Come on, say it loud.
Yeah.
Yeah, we can obviously we start because we know it's only one king, so we start from king. It's better, right? The time complexity will be O(n) squared because if there are n cells, then there are n square edges, and we visiting each vertex exactly once. We're using the hash scene, right? But if we start from horse, and then we need to find a king, so let's multi-source, right? Alright, listen to me. We start from the horse because there will be many horses, yeah? So at the beginning, here, if we start from the horse, then this will be executed. There will be multiple horses appended in the queue, right? And when we start at the beginning, instead of continuing a single king, we will have many horses here, many horses at the beginning, right? This could be many horses, right? Many horses. And then we can for each one we can expand its 8 kits, yeah, possibly 8 kits, right? And then we find the king, right? So look, there could be n horses. So the time complexity will be O(n) times n squared, right? But this m could be in the order of n, right? Because look, there are n positions on the board, and then could be m is smaller or equal than n, right? Yeah, got it? So this time complexity, which one is better? O(n) times n squared or O(n) squared? Which one is better?
Square.
Yeah, obviously, because they look you reverse it. Yeah, you reverse it. M you pick 1, right? Because we start from a single king. The space complexity. What's the space complexity? Are we using any space here? Sim and Q. So what's the space complexity? O(n), because look, yeah, sim. There are n vertex. Yeah, n vertex. So because we're using the set to store the number of vertex we have seen. So at most the time complexity is there could be n vertex in the hash set, okay, and the Q as well. Any questions so far? What's the subject we talk about today? Sorry?
Chess.
And what's the algorithm we're using?
BFS search.
And we also talk about what kind of BFS search? Multi-source BFS search. Previously, we have focused on the single source BFS search, right? Look, the binary search. We push the root. There's only one root. Yeah, level by level. Yeah. What's the BFS search of this order? This traverse.
2, 3, 4.
Yeah, that's it. And if now we basically today, no difference. It's just extra one. We have another 5 here. And what's the BFS search of this?
1, 5, 2, 3, 4, 6.
We're done. That's it. That's the takeaway today. Okay? And instead of doing that, we just instead of pushing one node, yeah, we just push the multiple nodes in the queue, right? We push the 1, 5 in the queue. Yeah, look, we push 1, 5 in the queue, right? And then we take one out, push all its kids 2, 3, 5, 4 here. And we take a 5 out, we push the kids 6 here. You see? It's the same. Yeah? It's the same, yeah? Okay, that's it for today. Bye bye. Goodbye.
How much was that?
Can you say bye bye again? Jump.
Bye.
Bye bye.